My name is Kirill Struminsky. I'll be running the first practical session today. And our plan for today is the following. At the moment, my assistants are distributing the problem sets, which also can be found at our GitHub. In the folder of the first practical session. So you'll be given a problem set, and you'll be asked to solve the problems and ask your questions and tell the solutions to our assistants. There are 4 of them here. They are Andrei, Artem, Dasha, and Ira over there. You can recognize them by their purple badges. And just to keep the pace, I'll be telling the solutions of the problems each 15 or 20 minutes. And also, I'll be describing the problem and our motivation behind this problem, just to make the practical session more useful for you. So let's begin. There are 100 sheets of paper that I printed, and if it won't be sufficient, you can download the problem set or just use the problem set of your neighbor. So I'll start with describing the first problem. It's a reference to a Harry Potter fanfic, and at the same time, it's the simplest probabilistic model where you can do Bayesian inference. A quick small comment about the notation. So I write here that the prior probability of survival is 1 to 100, and it means that the probabilities are 1 to 101 and 100 to 101, not 1% and 99%. I hope that this comment will make the computation a little more simpler. So I think that you should feel free about your pace. So if you think that you'll be able to solve everything in just a few minutes, okay, you may go. No. I think probably the whole problem set will take an experienced person. Well, it will take 20 or 40 minutes to solve if you've already seen the solutions or know how to solve them. Just 40 minutes to write everything down. I feel like we have to go on. And so I'm going to tell briefly the solution for this problem. So the hardest part about this problem is to parse the text and come up with a probabilistic model. As I've already told, the probabilistic model is as simple as possible. You have to declare 2 binary variables, one for Dark Lord being alive, and the second one for the dark mark. And then apply just the Bayes theorem. To compute x given y, you have to write joint probability over marginal probability of condition. Compute both things. So this one is given. This is 1 because you always see the dark mark is if the Dark Lord is alive. And then this is the prior probability, which is 1 to 101. And this is just the sum over probabilities for survival by probabilities for seeing the dark mark. So at the end, when we multiply by 101, we get the following solution. It's 1 over 21. So it feels like Dumbledore is pretty silly to believe that the Dark Lord is alive, because the resulting probability in this anecdotal model is still pretty low. Any questions? Okay, let's continue. So all the other problems from 2 to 5 are somehow related to multinomial Dirichlet model. This is a straightforward extension of model for Bernoulli experiments, which was described on the lecture. But unlike the Bernoulli model, where we have only 2 outcomes, now we have an arbitrary number of outcomes, which we denote by K capital. So in this problem, we are given a set of outcomes. So we throw a dice, see its face recorded as a number, and make n capital dice rolls. And then we use the following likelihood model. We define a parameter vector theta, which belongs to a simplex. And we say that the probability of outcome k at this particular dice roll is theta k. And the resulting likelihood will look like this. All the details about the notation are written down in the problem set. And I've been told that there's a small typo in nk definition, and here it is also. It has to be x subscript n, not x subscript I. So this is pretty much it for the problem setting. And I would also like to make a small comment that this problem is essentially a problem from frequentist statistics. Here we have a parameterized probability distribution. And the only randomness which we face is the randomness from dice rolls. We believe that the dice parameter is a fixed vector. And in this setting, we are just to infer this fixed parameter theta using maximum likelihood method. So now another 15 minutes to solve this problem. I think we have to proceed to get to the Bayesian stuff. Luckily, the next problem is devoted to the Bayesian stuff. So how do we solve this problem? I have to be honest, I'm going to cheat a little and to give you a simple and incomplete solution, because a rigorous way to solve this problem is to apply the Karush-Kuhn-Tucker conditions, which allow you to use both restrictions for equalities and for inequalities. And in this problem, we are restricted to theta that are positive. So therefore, the rigorous solution has to use Karush-Kuhn-Tucker method to find a stationary point and then give some arguments to prove that this point is maximum. Here I'm going to switch to another parameterization in which theta will be positive by default, and a small deception arises when we get to the border, because with this parameterization it is impossible to find a finite mu such that exp of mu is 0. So I'll say it again. Instead of using theta, I will use a new variable mu. That is a logarithm of theta, and mu will be a real variable without any restrictions besides the restriction that theta have to sum to 1. So this allows me to get rid of inequalities, inequality restrictions, and then just apply a simple Lagrange multiplier method that is applicable to only equality restrictions. So I use this parameterization, and then I write the Lagrangian function. Here it is, my likelihood, and the conditions, theta sum to 1. I rewrite the likelihood and then differentiate the Lagrangian function with respect to mu k and lambda. And after differentiation and solving the equation that derivative is equal to 0, I get that theta is nk over lambda. And the partial derivative over lambda gives me an equation that says that thetas have to sum to 1. Therefore, when I substitute this solution here, I get that lambda is equal to sum of n's. And as a result, we get a very, very natural solution for this problem. So the probability of dice coming up with phase k is the number of such results divided over the total number of outcomes, which, by the way, sums to n capital that we used in the problem setting. I'm not going to tell you why this stationary point is maximum, just to keep it simple. Are there any questions regarding this solution? Okay, so let's proceed. Now we're going to switch to Bayesian Rule, in which we believe that not only the observations are random, but there is some randomness hidden inside the experimental process, and we are not able to find there exists no point estimates for theta. Therefore, we will introduce prior distribution for theta and work with theta as a random variable that we do not observe. So first of all, we introduce prior distribution for theta. There are various ways to introduce prior distribution, and the one that is the most computationally efficient is to introduce Dirichlet prior, because this is a conjugate prior for the multinomial model. It means that if we want to derive the posterior distribution, we will be able to do it analytically. So the distribution looks quite scary. We have this product, which is quite simple, and it looks just like the likelihood we had in the previous problem. Due to this similarity, this prior will be conjugate. Besides that, we will have to restrict theta to simplex. That means that thetas have to sum to 1. And also we have to introduce some normalization constant, which is not a very simple function. Therefore, up to now, we will denote it as beta of alpha 1, alpha 2, and so on. This normalization constant in the problem set is defined as an integral of theta to alpha k minus 1 over the simplex. So now when we have the prior distribution for theta and likelihood, we can try to compute the posterior distribution over theta after we observe the data set. So this is the first part of the problem. A few comments on the second part of the problem. After you get the posterior distribution, you're asked to compute a thing that is called the posterior predictive. This is a rigorous Bayesian way to answer the following question. What is the probability of this outcome after we observed the data set and checked and corrected our beliefs on parameter theta? So the posterior predictive distribution looks like this. You're asked to compute this, and after you compute the integral, you'll end up with a ratio of 2 multivariate beta functions. And these functions are not easy to compute, and it's hard to predict something with this scary formula. So you're given an expression of beta function via gamma functions that can be used to simplify the answer further. So the final answer for this question has to be as simple as the maximum likelihood estimate. Not the same one, but as simple as this. And another comment on our schedule. I plan to spend 10 or 15 more minutes on solving this problem, then proceed to the fourth problem, and the last problem that is marked with star is considered to be hard, so I'm not planning to discuss it during the seminar, but feel free to catch me after the session and ask me for the solution or any tips how to solve it. I feel like it's time to discuss the solution of the third problem, because we have 15 minutes left, even less. And I really want to discuss the fourth problem. So let's go on. As I've already told you, Dirichlet prior is very, very handy because you can compute posteriors analytically. And it looks like Dirichlet prior is quite flexible. For example, these are densities for Dirichlet prior for three-dimensional vectors. And you can move the mode of this posterior to correct your predictions. But again, I'm sort of deceiving you, because as we've already seen, this distribution has only one mode. And this is a very serious restriction, because if you want to, for example, put a prior for an unfair coin, you have to have two modes. One mode for coin giving more ones, and one mode for coin giving more zeros. And a special case of Dirichlet distribution, as I've already told you, is beta distribution, which is also quite flexible from the first view. But again, you can't incorporate distributions that have densities that look like this. Oops. Two modes, impossible. But to solve this problem, there's a very simple fix to solve this problem. Just replace your Dirichlet priors with mixtures of Dirichlet priors. And for example, you can encode the shape I've already drawn with a mixture of one density that looks like this, like the orange density, and its symmetrical transform. You can have two modes with a mixture of Dirichlets or betas. So let's proceed to the solution of the problem. The only thing that we do here is just apply the Bayes rule. Let me grab a pointer. We're given with the likelihood. We have prior. The only thing that we don't know is this denominator, which is also called evidence. You'll encounter it later multiple times. We have to compute evidence, and we do it by this sort of integration. We write the joint probability for data set and for theta, and then integrate theta out. I substitute likelihood, then I substitute an expression for Dirichlet prior. Here it is, Dirichlet prior, normalizing constant, and integration with respect to on simplex. In this case, the indicator is not needed, it's always 1. So this is the integral, and the main trick of this problem is not to compute the integral. This integral is given to you as the definition of beta function. An integral over simplex of product of thetas at some degrees is just a beta function. And after all, we see that this integral is equal to beta function with arguments alpha plus n1, alpha 1 plus n1, alpha 2 plus n2, and so on. So this was the trick. We have this ratio, and then we can substitute this ratio into the Bayes formula because we now know everything. And Bayes formula will look like this. Some quantity, some quantity, some quantity. These betas cancel out. And the formula we end up with is just a Dirichlet distribution for corrected parameters alpha plus n plus n. So I denote it here as alpha prime. A question to think about: was it necessary to compute P of D given alpha, or we could derive it just by knowing that this is the conjugate prior and so on and so on? I'm not going to dig into details, but try to think about this question later. So now we compute the posterior predictive. I write the integral as in the problem setup. Then I substitute P of theta with expression for Dirichlet prior, this likelihood with this value, because this is just the probability of outcome k. And then I integrate. Again, I see that this integral is just a beta function written for different arguments. This time I just correct one argument and add a unity there. And the answer to this problem is this ratio, which can be then simplified using the expression of multivariate beta function with gamma functions. So the expression is in your problem set. Here it is, I write it, and then I use the second property of gamma function to simplify the answer even further. I cancel out these gammas, and for these two gammas, I rewrite this gamma using the property as gamma of the sum and the sum. And these gammas I rewrite, this gamma I rewrite as gamma of this argument times this argument. Everything else cancels out, and we end up with this answer. It is also very natural because we have prior parameters alpha. Then we observe the dice rolls, correct our belief about theta, the dice parameters, and our new prediction blends in our prior parameters and our observations nk. A very simple answer. However, the derivation was pretty heavy. Now let's proceed to the last problem. Some of you already started tackling this problem, and there has been a very popular question: how to deal with delta function. Again, I'm not going to dig into details because proper definition of that delta function is quite tricky, but I'll provide you with a very, very simple equation that you can plug into your derivations and everything will work out. So the question is the following. If we want to compute an integral of a delta function, is the size normal? Does everybody see? Okay, so if we want to compute an integral of delta function times some other function, the answer will always be the following. We'll end up just with this function, f, at point theta prime. So you may use this equation to solve the first part of the fourth problem. And the intuition behind this is the following. that we have two functions. For example, some f of theta and something that is almost everywhere 0, but at point theta equal theta prime, it has an arbitrary large value. And what is more, integration of delta function gives you unity, and when you multiply this delta function by the value of function f at theta, you'll end up with theta prime, theta equal to this value. Guys, I feel like it's time to have lunch, so I'll give a few more comments on the fourth problem, and then I'll finish the practical session. So sometimes, even though we are Bayesians, we're not satisfied with node point estimates. For example, imagine that you have to predict whether tomorrow is going to rain or not, and you have to decide to take an umbrella or not. Even if you have an amazing prior and amazing history of observations, you'll end up with a Bayesian estimate that says, well, with 50% probability you'll have to take an umbrella, and with 50% probability you don't have to take an umbrella. And tomorrow you'll have to make a final decision. You don't have options to take or not to take with some probability. You have to make a decision. So Bayesian decision theory suggests to introduce some loss function that says that quantifies the amount of regret for making this decision. And then you're suggested to make a decision that makes you regret the least. And this is a typical way to deal with point estimates in Bayesian framework. These two examples are classic. For the first loss function, you'll end up with mode of distribution, and this problem suggests you to find the mode of Dirichlet distribution. And for the second loss function, you'll end up with mean of Dirichlet distribution. So you have to find what is the mean of Dirichlet distribution. Spoiler, you've already computed both values in previous problems, but you don't know about this. So that's all for this session. It's time to have lunch. If you want to ask questions about any of the problems or about any of the problems we solved or about the fifth problem, feel free to catch me. Thank you.